The history of the neutrino starts with the theory of nuclear radiation pioneered by Wilhelm Röntgen in 1895. To become more stable, a nucleus will drop down to a lower energy state, emitting excess energy in the form of alpha, beta, or gamma radiation. Because a specific nucleus will only ever exist at certain energy levels, radiation will only ever be emitted at certain energy values. Physicists proved experimentally that alpha and gamma radiation fitted this new theory, with their energy spectrums looking like this. However, for beta radiation, which is the emission of electrons from the nucleus, the experimental results did not match the trend. Beta's energy spectrum should have looked like this, with a single energy value, but it was in fact continuous, meaning an electron could be emitted with a range of energy values. Consequently, many scientists desperately tried to solve the problem, but it was not until 1930 that Austrian physicist Wolfgang Pauli came to the rescue, proposing the existence of a neutrally charged, extremely low mass particle which would be emitted along with the beta radiation, taking away some of the energy that the electron would have had. This particle would be called the neutrino. Then, in 1933, Enrico Fermi proposed the theory of beta decay, where a neutron decays into a proton and an electron-neutrino pair is emitted. Unfortunately, the neutrino was very hard to detect. In fact, it is known as a ghost particle because the neutrino's almost negligible mass and zero charge means that it hardly interacts with matter at all. Despite this, in 1956, two American physicists, Frederick Rines and Clyde Cowan, verified the existence of the neutrino particle in the Savannah River experiment. So, what actually is a neutrino? Neutrinos are fundamental particles, meaning that they are part of the standard model of particle physics, which describes all the constituents of matter that cannot be broken down into anything smaller and how they interact. There are three types or flavors of neutrino: electron, muon, and tau. They all have zero charge, spin of a half, and the original standard model predicted them to be massless. In 1970, physicist Raymond Davis Jr. became the first to detect solar electron neutrinos and found he was measuring far too few of them, indicating our understanding of the neutrino was wrong. The theory of neutrino flavor oscillation was developed in order to explain this discrepancy. Neutrino oscillation is a quantum mechanical phenomenon which requires neutrinos to have mass. A neutrino of a specific flavor can later be measured to have a different flavor, and the probability of measuring a particular flavor for a neutrino varies periodically as it propagates through space, as given by this equation. In 2015, the Nobel Prize in Physics was given to Takaaki Fujita and Arthur McDonald for the discovery of neutrino oscillations. You may think that neutrinos are unimportant, insignificant particles, but they have led to many important developments in physics and will surely bring us many more in the future. The result of neutrinos having mass was not predicted by the standard model, showing us that the modern theory of particle physics is incomplete. And as to insignificance, after packets of light called photons, neutrinos are the most abundant particle in the universe, with there being on average 1 million neutrinos chilling in every pineapple. So despite the neutrino mass being less than 1,000,000 times that of an electron, the combined mass of every single neutrino is estimated to equal the mass of all the visible stars in the universe. So our little friend the neutrino packs one hell of a punch.